All right, everyone. So for this lecture, we're going to be taking a look at the kinds of measurements that we can do with semiconductor devices. Because up to this point, we've sort of talked about the fundamental physics of these devices and some of the quantities that we're interested in, like carrier concentrations and effective densities of state and things like that. But we haven't really told you how to actually measure any of these quantities, right? We just tell you that they exist. So hopefully that changes today. My plan here is to kind of go through a couple of different measurement techniques that have been used to look at some of these different measurement or different quantities. So hopefully we get a better understanding of what a laboratory experience is actually like doing semiconductor measurements. So the first thing I think that's easiest to talk about is the light absorbing properties, the spectroscopic properties of semiconductors. So you're probably familiar with this. I know we've talked about this in the recitation, but we'll just go through it anyway. So absorbance in a solid is expressed basically the same as what you would expect for Beer's law, right? So you probably remember from like intro chemistry that you have this relationship of absorbance to the natural log of the transmittance or the incident versus the initial light intensity. And that is equal to, you probably remember, like ECL. So there's the molar extinction coefficient multiplied by the concentration and then multiplied by the path length. So hopefully that's not new information for you, but this is good for basically any molecular system. You've used it for like every spectrometer you've ever touched. And it's a pretty simple law, but it's a pretty good one. So what it basically says is that the amount of light that is absorbed is proportional to, first of all, how good each of these molecules or atoms is at absorbing that wavelength of light, multiplied by how many of them there are per unit area, multiplied by how much area or volume there actually is, right? So what it's saying is there's the molecules are this good at absorbing light, and there are this many of them, so we should expect this much light to be lost. That's all that means. So we can extend that into solids, but for a solid, you can't really vary the concentration anymore. Like you can, but it's tricky. And for most laboratory purposes, let's just say it's impossible to vary the concentration. So what we're going to do, since now the concentration here is a constant and the molar extinction is a constant, why don't we just combine them? So we're going to combine them into a single constant, alpha, which is called the absorption coefficient. It's the same as the molar absorptivity multiplied by the concentration, and it has units of inverse centimeters. So now our Beer's law is even simpler. The absorbance is just alpha times L. So just like in a molecular system, alpha is a function of wavelength. So you're not going to get the same absorbance at every wavelength, right? One of the key differences is that unlike in a molecular system where you would get maybe like a Gaussian distribution based on like in different areas depending on the different molecular orbitals that you're exciting to, in general, due to the continuous or the continuum of states that's present, alpha basically only increases. It's not 100% true, but in general, you can expect as the wavelength gets shorter or the energy of the light gets higher, in general, the semiconductor only gets better at absorbing that light. So yeah, if that's confusing at all, think about molecular orbitals. So we have like these HOMO and LUMO levels. And if you excite it just the right amount, you'll go right from one to the other. And then just because molecules have different energy distributions, you're going to get, instead of a line, you're going to get Gaussian distributions. But if you have atomic species, you will actually get lines. So if you have energies that are above that, you're not going to absorb it because there's no state for you to absorb that. But for a semiconductor, as long as you are above the band gap, you're going to absorb it. You might absorb a whole lot of it or not a whole lot of it, but you're going to absorb it because there is a state present. Okay, and now I mentioned this, that above the band gap, you're going to absorb it. But what if you're below the band gap? If you're below the band gap, you don't have enough energy to go from the highest possible valence band energy to the lowest possible conduction band energy. So there's no states in between there, at least for our idealized system. So so that means that there's no way to absorb anything. But that also means that as soon as the absorptivity starts to really increase, that must be the band gap, right? Once we start absorbing, that has to be where the band gap is. That's the only way we're going to get absorbance. So that means that we can measure the band gap of a material spectroscopically. All you have to do is take your sample and just put it in a spectrometer. So you just have some I naught out here with I. You just measure whatever that is. You monitor how much light is absorbed at all these different all the different wavelengths. And as soon as it starts to kick up, there you go. That's the band gap. And then you just have to convert the energy or the wavelength of the light to the energy. So on this example on this example plot here, where I'm plotting alpha against wavelength, right there, right as soon as it starts to tick up, right? We're not looking here where the absorbance is already maxed out. We're looking at right where it starts to absorb. That is your band gap energy. So that's pretty convenient. It's an easy thing to do, and it works pretty well. But not only can we tell whether or not, or where the band gap is, we can also tell whether it's a direct or an indirect semiconductor spectroscopically. This one's going to be a little bit more qualitative than quantitative, where, you know, with the band gap, we can just say like right there, that number, that's the band gap. The indirect versus direct, we're sort of looking at what the graph looks like. So if you recall, an indirect band gap species is going to have pretty low absorbance close to the band gap. And the reason for that is that if we look at our E versus K diagram, now let's see, this is going to go down here, and we're going to have that like there. So this here is our band gap, right? So we have our lowest conduction band, highest valence band, but they are not right on top of each other in K space, right? Which means that in order to do this excitation, we need something to excite it in energy. So we need like a photon. But we also need something that excites it in momentum, or that changes its momentum, like a phonon. And because you need two things to happen at once, it's rarer. Doesn't mean it doesn't happen, but it's rarer. So the absorbance close to the band gap is pretty low for an indirect band gap semiconductor. Think of it like a D to D transition. But once we start getting more and more energy, you start to be able to, like, say, excite these states here and like these states. And so the absorbance gets much, much higher as you start to increase the energy, and it basically saturates to be effectively as good as a direct band gap semiconductor. Get rid of all that. Okay. So to give you an idea of what that would look like, so we have here a direct band gap and an indirect band gap semiconductor. So you can see that for this indirect band gap semiconductor, the absorbance sort of stays low, close to our band gap, which, remember, is right there as soon as it starts to take off. Where in sort of the same region, there's our band gap for the other one. For our direct semiconductor, we have a really high alpha value, you know, like 10 to the 5. So that's sort of how you can tell the difference there. So yeah, now at this point, I should be able to hand you a semiconductor sample, and I could tell you, I want you to figure out what the band gap for this semiconductor is, and I want you to tell me whether it's a direct or an indirect band gap. And now you should be able to do that. You just stick it in a spectrometer and you measure the alpha values over a range of wavelengths, and you should be able to find the band gap energy, and you should be able to check the graph behavior, or the spectroscopic behavior, to figure out whether it's direct or indirect. All right, now we're going to get into something a little bit new. We're going to get into resistivity and Hall measurements. So these measurements are used for figuring out the carrier concentration in our semiconductors. So this is one of those things where, it's a nebulous idea that we talk about in lectures, saying we can have this concentration of electrons and concentration of holes. And I mentioned that if you increase the concentration of electrons or holes, such as by doping, you've increased the conductivity. This is where we're actually going to talk about how much it increases the conductivity, and how you can measure the conductivity to figure out how many carriers there are. And from that, you can use all those fancy relationships to find out all sorts of stuff, like the effective density of states near the band gap. You can figure out like where the Fermi level is, all that kind of stuff. How do we do this? We're going to measure something called resistivity, which is like a fundamental material constant that says how easy it is to move charge from one place to another. Now, it's important to note that resistivity is not the same as resistance. Think of it as like a resistance density, right? Because if you were to take a sample, let's say like a wire, right? Yeah, so I've just got like a wire here. And this wire has some resistance R. So that's a resistance R over this length, L, right? If I make that wire longer, my resistance increases, right? You can think about this also as like, if you've ever tried to, well, yeah, think about it like this. Think about it like if I've got a sample here, if I measure the current here and here, and then I measure the voltage or the resistance between these 2 points, that's going to be different from where I measure the resistance between these 2 points, because it's further away. It's harder to, it's physically harder to get the charge all the way over there. And that's how we measure resistance. Resistivity, you would get the same resistivity at these 2 points as you would these 2 points, because it's sort of a fundamental material constant. All right, let's get rid of this. And we'll talk more about resistivity and drift and currents and all that in the next couple of lectures. But for now, let's just take this as it is. So resistivity is defined as the applied electric field divided by the current density. And what we're going to do is apply a voltage to our semiconductor and then just measure the current. And so by applying the voltage, we should know the electric field. It's a pretty fundamental relationship. So we know the electric field strength. We know the current because we're measuring it. And so we can then just measure the resistivity. Now there is this relationship here where the drift current is equal to the fundamental charge times the mobility of electrons here times the concentration of electrons plus the mobility of holes multiplied by the concentration of holes. And by the way, these are 2 parameters which we will get more into when we talk about like Fick's laws and diffusion, making junctions. But think of it like, again, how easy it is to move these things around in our crystal, multiplied by the electric field strength. So then combining those 2 relationships, we get that the resistivity is equal to 1 over the fundamental charge times that mobility concentration thing. Okay, so if we're working with a doped semiconductor in the extrinsic region, recall that, let's say we're doing an N-type, and we have N-type dopants. We have a bunch of donors in our crystal. That means that the concentration of electrons is approximately equal to the concentration of our donors, which should be way bigger than the concentration of holes. Or for p-types, it's reverse. So the concentration of holes is approximately equal to the concentration of acceptors, which is much, much bigger than the concentration of electrons. So we can simplify that equation up there. So that resistivity is essentially equal to 1 over fundamental charge times mobility times concentration of our dopants, which you should know because, ostensibly you've doped it, either you or the company you bought it from, and you can measure that concentration. So you can do that if you know the concentration. If you know ND, you can measure the mobility. Or if you know the mobility, you can measure the resistivity, and you can get the concentration of dopants or the concentration of electrons and holes. So the way that you actually do this measurement is using something called the 4-point probe technique. So it's sort of, it's exactly what it sounds like. What you do is you take literally 4 probes that are equally spaced. So they have this, this spacing S here. They're all evenly spaced. And you just make contact with the top of a semiconducting material here. And then what you do is you apply a current through the outer probes, and you measure the voltage through the inner probes. And then from that, you can kind of plug that into some of these relationships here. Like you can get the drift, like you can use the voltage to figure out what the drift current must be. And from that, you can figure out the resistivity. So we were using 4 probes, but why not 2, right? We can measure voltage and current. And we would only need like 2 probes for that, right? So why do we use 4? The main reason is because, in fact, we can't really use 2 and get accurate measurements. If you're familiar at all with electrochemistry, you can think of it as why do we use 3 probes in electrochemistry, right? So we would have like our counter electrode, which is where the current comes from. We have our reference electrode, which is how we measure the voltage, and our working electrode, which is actually like doing the chemistry we care about. Right, so the current is flowing between these 2, but we're measuring the voltage between those 2. So there's a couple of reasons. One, so for in electrochemistry, it's because that is a very stable voltage, and so it's not going to change very much. Because when you put current through a material, a lot of times the voltages can be a little bit unstable. So that's part of it. But the main reason that you do this in a 4-point arrangement is that you have to consider the fact that there's such thing as contact resistance. So when you are actually physically touching the probe to the surface, make sure it's actually physically touching there, it's not a completely lossless contact. Especially with semiconductors, things can get kind of annoying. So we can approximate this thing as, let me make sure I draw this correctly, contact resistance. Now, there's going to be one for each probe. And then, of course, there's going to be resistances in the material. So through the outer probes, we're passing a relatively large current, right? And from Ohm's law, right, so P is equal to IV, I squared R, so V equals IR, I believe. Yeah, I believe that's right. So if we have a large current going through these contact resistances, even if they're kind of small, there's going to be an extra voltage, right? So there's going to be an extra voltage drop that is not through our material. We're going to get voltage drops above the material, not through it. That's bad. We want to isolate those, the voltage that's through the material, the resistance of the material alone. So we use these middle contacts where there is very, very, very tiny amounts of current flowing through them, right? We're just essentially contacting them like we would do with a voltmeter. So because there's very little current flowing between those two, just using our same relationship there, the voltage drop from the contact resistance is going to be tiny to the point that it doesn't matter. And so the only resistance that matters is the resistance through the material. And that's how you're measuring. That's why we're using 4 points. That's how we're measuring this. Okay. So then you measure the resistivity using this equation here. So we know our spacing, we know what the voltage is through our inner probes, we know what the current is through our outer probes, multiplied by this factor of 2 pi. And then there's this correction factor, because kind of what you're saying here is that there's this linear relationship between the voltage and current that you could then say, like, essentially what you're saying is like V is proportional to resistivity times current. So if you were to plot, current versus voltage, you would expect some linear relationship where the slope is related to the resistivity. That's not exactly what happens in real materials. In real materials, it does like something like that. So at each point, you need to make like a slight correction. And that's all that FC is. It's just a correction factor to make sure that you're getting the right value. And these are tabulated. You can get those no problem. So from that, we get our resistivity. And from our resistivity, we just plug in our fundamental charge, and then whichever constant we know, either the mobility or the concentration of dopants, and we know the other one. So that's great. However, sometimes 4-point probes are a little bit unreliable. So one of the key cases for that is gallium arsenide. So gallium arsenide. There's a problem with making contacts to gallium arsenide. So if most metals, if you contact it, it doesn't make an ohmic contact. It forms sort of a diode, which we'll get into. But that just means it's bad for doing these measurements. So you need another way to do it. So you can do something called Hall measurements. And also you can do Hall measurements even if the 4-point probe works. And a lot of people do, because then you sort of have 2 measurements of the same thing. It's a little bit more reliable. So the way a Hall measurement is set up is you have your semiconducting sample right here. We're going to pretend it's just a chunk of semiconductor. And you're going to apply a voltage. So we have VA for V applied, which is going to cause a current to flow through. And that we're just going to ground it out. This, if you're not familiar with electronic notation, that just means we're connecting it to ground. It just means we're like literally sending it into the ground. We're not worried about where that goes. The current that's called a current sink. So we're just applying a current through our material, but at the same time, we are applying a magnetic field perpendicular to that. So we have the current going one way, we have the magnetic field going the other way. And then what we're doing is we are actually going to measure the voltage drop across the perpendicular faces to both the B field and the current. So just to like sort of draw it out graphically. So the B field is going this way. The current is going this way. And our voltage that we care about is across this axis. So perpendicular to both. Why exactly it does that, you can look into it yourself if you care. I claim that for the purposes of this course, nobody cares. But if you do, you can look it up and just look up the Hall effect. So this voltage that you measure is called the Hall voltage. And you can use it in collaboration with a bunch of these other measurements here to figure out the carrier concentration. All right, so we are applying a magnetic field B, a current I. We have a width, a length, and a like a thickness, right? So we want to calculate this thing called the Hall coefficient, which is R sub H. We can calculate the resistivity, which you can do when the magnetic field is 0. And then from that, we can get what's called the Hall mobility. So we already mentioned the regular mobility mu, but this is going to be the Hall mobility, which is saying like how easy it is for this to move in these conditions with both current and magnetic field applied. And they are measured through these equations here. So the Hall coefficient is measured from the Hall voltage times the width divided by 10 to the 8 times the current, the magnetic field strength times the current. The resistivity is from the applied voltage divided by the current times the width and diameter and the length, all that. So remember, the resistivity is like the resistance, which would be the V over I, over like it's like the resistance density. So you're kind of taking the volume of, you're taking the resistance, and then you're also taking the volume of your crystal. So resistance and the volume of your crystal there, and that's what's giving you that like resistance density, which is what resistivity is. And then you can get the Hall mobility just by dividing the two. Okay, now we have all of those components. Then we just need this extra little thing called the Hall factor, which is the difference between the Hall mobility and your regular drift mobility. For most things, this little r sub h is about 1. And it's usually close enough to 1 that even if you know nothing about your crystal or nothing about your semiconductor, you can just say it's 1 and be like pretty close. You're not going to introduce that much error. So generally think about that as like kind of 1, but it's not actually, and you can measure it if you get all this very precise. And from there, you can get the concentrations of your carriers. So from there, we have our RH, R sub H here, which is our Hall factor, which is equal to our Hall coefficient, which is equal to our Hall factor, which is about 1, divided by Q, our fundamental charge, times, in this case, our concentration of holes, or, and then this didn't get finished, the Hall factor divided by Q times N. Right, so if you do a Hall measurement, you will be able to measure this, these, and that. And then of course, you'll know the dimensions of your crystal. So from that, you'll be able to calculate all of these guys. And from that, you'll be able to get out both P and N, which are your carrier concentrations. And then recall, if you're working with a doped carrier, P is going to be approximately equal to N sub A, and N is going to be approximately equal to N sub D. Right? So hopefully now you have an idea of the kinds of experiments you can do to pull out things like carrier concentrations, band gaps, and like figuring out what type of band gap you have. So if you were to be thrown into a lab tomorrow, you would be able to figure out how to do some of these things, or at least have the right terminology to ask someone who knows how to do these experiments how to do it. So that's going to be all for this one, and I'll see you on the next lecture.